I'm a big believer in what's called active learning. All right? Now, you sitting there watching me, particularly since it's hard for you to understand me, it's not very useful. Okay, so we're going to do a little exercise. So the purpose here, 2 or 3 purposes. One is to help you practice listening and understanding English. That's part of the reason why you're here, is to do that. So the second goal is for you to practice your artistic skills, your drawing skills, because that's very important in order for you to connect the words in a problem, for example, to what's really going on, the situation. Okay? And the third is to be able to go from those 2 things to some physics understanding, to draw some understanding for it. So I am not going to write anything on the blackboard for the next 5 minutes or so. I'm going to tell you what to do in words, orally. The situation was the following. So I'm going to say the words for the problem, all right? And then I'll tell you what to do with the problem. So we had a particle, and this particle had a force acting on the particle. Okay? And that force was given. It was given as having a x component of A, little a, and a y component of B. So that was the force. It was a vector. The object had a mass m. And this object moved, due to the force, from a speed of v1 to v2. Okay, so it changed its speed. And it went a distance d during that time. When it changed its speed, it went a distance d. And the question asked for you to determine the direction of the change in position, or the direction of the displacement vector. All right? I don't want you to actually do that yet. I want you to follow my directions on how to do it. Okay? Because there was a lot of confusion in the quiz, I think even what was being asked. All right. Draw an xy axis. Xy axis. And don't make it too small. Now, we're told that both A and B for the force are positive. So draw on your diagram that you have so far an arrow representing the force vector F. So draw that. Now I want you to choose a point on your diagram which is going to be the place where the particle starts with this velocity, with this speed v1. In principle, you can choose any point on the diagram. But we might as well make life easy and choose the origin. So make a big dot right at the origin. And that's going to be the starting point for this particle's motion. Everybody good? So, all right. Now, you want to draw a vector representing the velocity v1. The tail of this vector should be at that dot. Right? Should be at that dot, because we want the velocity, the initial velocity, the starting velocity, v1, to be at that dot. Again, you could draw it any way you want, except there's one choice you cannot use, and that is that vector v1 cannot be in the same direction or opposite to the force. Any other direction is fine, but not along the force. So draw a second vector, this v1, the velocity v1, with its tail of the vector, is at the dot to indicate that that's the velocity at v1. It's probably better, so you might want to change your v1, your vector v1, so that it's not too close to the force F, because the next step will make it harder if it's too close. All right, so try to make your v1 point a little further away from F, not too close to it. Now comes the hard part. We're going to use some physics now, some intuition, some thinking. The next step is to draw the trajectory of the particle over a brief period of time. Now, you don't know anything, but you do know two things. You have the velocity vector initially, and you have the force. And you should know what forces do to velocities. Right? So you should know whether the particle is going to bend away or towards or how it's going to go. So draw a path for the particle. Draw a path for the particle that is possible given your force and given your initial velocity. Okay? So draw that path. Everybody set? Now, choose a point on this path that's going to represent the particle when it has velocity v2. It could be anywhere on the path, but probably not too close to v1, because it'll be hard to see. So choose a point on the path where the velocity will be v2. Okay, so all you got to do is put a dot there. So at that dot, now draw a velocity vector that's going to represent v2. It has to be consistent with that vector. And you could tell whether, based on your diagram, it's going to be different for different people. That vector v2 might be smaller in size or bigger in size than v1. It'll depend on where you drew the force and the initial velocity. Okay, so draw that vector v2. All right, good. All right, now, everybody done that? Did that? All right, now draw a vector from the initial point to the final point. That vector is the displacement vector. That's the change in position. So draw that vector. And you know the size of that vector. What's the size of that vector? D. We gave you that size is D. But we don't know its direction. So now you have the picture. We haven't even started the problem yet, really. This is not really what the problem is about. The problem says, determine a possible direction of the change in position using the work kinetic energy theorem. So we have not yet used the work kinetic energy theorem. So I want you to write down what the work kinetic energy theorem is that would be relevant to this case. And when I mean relevant, we know that the force is a constant force. All right? So when we write down the work kinetic energy theorem, we can assume the force is constant. So write that down. And then you can write down what that equation is in terms of the variables that were given. D, V1, V2, etc. Right? But first, just write it down. Make sure you have it there. And I'll check. We'll check to make sure you have it. I want you to check what you wrote for the work kinetic energy theorem. Make sure things that are vectors have vector signs on them, and things that are not vectors do not have vector signs on them. Like we were given the speed v1. That is not a vector. Speed is not a vector. Velocity is a vector. Okay, so make sure your equation looks right. In your work kinetic energy theorem, you should have a dot product, which you may have already calculated out what that dot product is, right? Dot product is between what and what? The F vector, the force vector, and the displacement vector. So when you take the dot product, you get the magnitude of one vector times the magnitude of the other times the cosine of theta, some angle. On your diagram, identify what angle that is. So now we're almost done, because we want to get our answer. We want to express the angle in terms of given quantities. For example, F, the magnitude of F, you can figure out, right? And we know V's and we know M. All right, so write down theta, the angle, equals something. And what it equals should be quantities that were given. What we're given is the components of F, A and B, the two speeds, V1 and V2, the distance D, and the mass M. So your answer should be in terms of those quantities. So see if you can do that. So at this point, all right, if you have, I'm going to write the answer down, if I remember it. So let's say 1/2. And all right, I think that's it. Is that right? Yes. So if you got to this point, that's what you're supposed to get. Now, some of you actually, a few of you got that, but on your diagram, you labeled theta wrong. I was probably generous and gave you credit anyway. All right? But most of you did not go through the process we went through just now, drawing the picture. And hopefully you can see how crucial that is. Without a good picture, it's hard to know what the angle theta means. So a picture tells you so much more than words do. The words you write down are really expressing mostly, all right, laws of physics or perhaps something about the motion. But the picture, a good picture, can save you a lot of words. And pictures are the same in English and Chinese. So drawing a good picture is important. So I want to suggest approach when I'm talking. Number one, it's probably a good idea for you to at least skim over the lecture notes before class. And I always have the lecture notes available before class. So the lecture notes that are online now already talk about momentum, conservation of momentum, collisions, all that I'm going to talk about today. All right? So it's a good idea to look at that. Now, what I would like you to do, or what I think you should do, which you should want to do, is I'm going to say things. I'll try to say it slowly. And I want you to predict what I'm going to write on the blackboard. So in your head, think about what I'm going to write on the blackboard. I'm going to say it, and then I'm going to write it. And between them, try to think about what I'm going to write. If you do that, then your mind is active, rather than just sitting there like you're watching TV. Okay? Everybody got that? All right, so let's try that. So we're going to talk about two concepts, impulse and momentum. All right. So I'm going to define momentum. Okay? So you all know how momentum is defined. So you should know what I'm going to write on the blackboard. So the momentum, P, is equal to the mass times the velocity, V. Okay? All right. So in your brain, if you had that in your mind before I wrote it, hopefully there's a surge of a certain chemical that makes you feel good. Serotonin? Yeah, probably. And all of you want to have lots of serotonin going through your brain. Okay? You want to feel good. All right? So try to predict what I'm going to say next. All right. So the next thing I'm going to do is rewrite Newton's second law using momentum instead of velocity. All right, so here's what that looks like. I'll write the words, and then you should know what I'm going to write next. Okay, so that's Newton's second law with momentum in there instead of velocity. You have to think about what Newton's second law is, and then imagine replacing it. Now, there's an assumption I'm making by doing that, writing it that way, and the assumption is that the mass is constant. It doesn't change with time. All right? So that's why I can take the derivative of the momentum and put in mv, and I get m dv dt. I do not have a term v dm dt, because I'm assuming m is constant. Now what we want to do is, if you remember, the work kinetic energy theorem came from integrating that equation with respect to position. Now I want to integrate it with respect to time. Okay? So if I integrate that with respect to time, all right, let's write down what that looks like. So first I'm going to multiply by dt on both sides, and then I'm going to integrate. So what I get is the integral dp equals the integral f net dt. Okay? Now I have to put limits of integration. So I'm going to do that. I have some p initial, some p final. I have a t initial, t final. This thing here has a name. It's called impulse. And it has a symbol I. So the impulse has a symbol I. This thing here, we can actually do the integral. because it's a trivial integral. So all it is PF minus P initial. Or we can sometimes write this as delta P. So the impulse momentum theorem just says delta P equals I. It's a vector equation. All right, so why do we do this? You know, when I was an undergraduate, I'm not even sure if they even mentioned this, but this actually gives us some insight. How many of you know what an airbag is in a car? You all know what an airbag is in a car? Airbag in a car. When you get in an accident, it blows up. All right? My own son was in an accident where his car was totaled. It was a hit and run by somebody who ran a red light. He went to the hospital. He had not a scratch on him because of the airbag. If the airbag wasn't there, he would probably be dead. Okay? So these airbags are very important. What do? Think about the change in momentum. You're driving, and then suddenly you come to a stop due to the collision, the car crash. So your change in momentum of you is the same whether you have the airbag or not. So what changes? Time. No, the impulse is the same. Impulse is the same, but what changes is the time. So I can write this as some kind of F net average times delta t. All right, so this is what you can write out in terms of the impulse. The impulse is the same. What the airbag does is it lengthens the time, reduces the force. So instead of hitting the windshield at a very high force, you hit the airbag at a very small force. But at the same time, the time of the interaction is lengthened. Okay? So that's the important way of thinking for impulse. Another example. If I throw a ball against the wall and the ball comes back with the same speed, if I look at the work kinetic energy theorem, I learn nothing. Doesn't tell me anything. But the impulse momentum theorem, I see that the momentum changed. Even though the speed is the same, the momentum changed. Why? Direction. The momentum this way minus the momentum that way. Or the reverse. The momentum that way minus the momentum that way if I throw it against that wall. Right? So it has a momentum going this way initially and a momentum coming back the other way. So the change in momentum is not zero. So there was an impulse delivered to the ball. Impulse came from the wall, from the force of the wall on the ball. So another important way of thinking is that what forces are about is delivering impulses to objects. So forces deliver impulses to objects. Now, let's say there's only one force involved, just to make it a little simpler, in the interaction. All right? Can you put your hand up? So I'm going to slap his hand. All right? So I slap his hand. All right? I'm sorry if I hurt you. All right? All right, so I slapped his hand. I gave him an impulse. There was one force, my hand on his hand. Did he do anything to me? Yeah, what did he do? Yeah? Is the force the same on me? Yeah, Newton's third law. So my force on him is equal and opposite force on me. What about the impulse he gave me? Is that the same or different? Same. By Newton's third law, if I give you an impulse, you give me an impulse. Equal and opposite. Okay? So that's very important. So we can use this feature if we can compute the impulse. All right? Maybe we know something about the force, and we can integrate to get the time. Then we can get the change in momentum. So if I know the initial velocity, I can easily find the final velocity just by using that. If you're not comfortable doing integrals, I'm not going to actually ask you to do any. It's just the area under the force versus time curve. So let me just draw an example. So if I have something like this, all right, the impulse is the area under this curve. Let's say from here to here. So that's all it is. Just calculate that area. All right? So there's one homework problem where you have to do that. You don't have to actually do any integrals. You can just estimate the area under the curve. All right, so that's the impulse. Now, related to the impulse, so you see, if I exert an impulse on you, and you exert an impulse on me, it's equal and opposite. So imagine we have a bunch of particles, and the only interactions for those particles are between themselves. So particle A interacts with particle B interacts with particle C with A, etc. But there are no interactions with anything else, only interactions between the particles themselves, not between any external objects. Or we imagine we're interested in the interaction over very, very short times so that the impulse delivered by external forces is negligible. Okay? So for instance, when I play pool, I worry about this, and I look at the interactions, how when the cue ball hits another ball, and then I want to see how the ball moves off. There is the table there, and there's gravity, and all these other things that are influencing things, but the time of interaction is so small that those are negligible during the collision. So I don't have to worry about it. All right. So what does that mean? So what I just said is delta P I for a whole bunch of particles is 0 if the system is isolated or the impulses due to external force are negligible. So this is if system of particles are isolated. So that means F external equals 0. There are no external forces. Or I external, the impulses, is negligible, approximately 0. Okay, so if those are the case. So under these circumstances, notice what I have. The change in the momentum of all the particles is equal to 0. So now I can say, let's say particle A initial. Oops, let's not use I. Let's use J. So I can say particle I initial particle B initial, etc., is equal to particle A final plus particle B final plus etc. Okay? Everybody know what I mean by these dots? If there are more particles, then I add those moments. Notice this is a vector equation. So that means it has to be true for the x direction and the y direction and the z direction, if you have 3 directions. Okay? All right. So this law here is called the conservation of momentum. So this is conservation. So anytime there's a collision or explosion, that's what you use. You use that. Right? Hopefully you're given enough information so you can calculate things. All right, let's do a typical example. You have a car that's sitting at a stop sign, and a big truck comes by, slams into that car, and sticks to it. Sticks to the car. So what is the final velocity? So we'll say the initial, we have the car mass, we'll call it m, the truck mass, we'll call that capital M, and we'll say the initial for the truck is given. Right? And the question is, what is the final for truck plus car? Right? So we're imagining that the truck and the car collide and stick together. All right? Which is somewhat realistic. All right? So we want to use conservation of momentum. All right? So everybody write down what they think this means for this case. You have all that. We want to find VF. What does it mean? We're in one dimension. Just head-on collision. That's pretty easy. Pardon? Initially, it's sitting there. It's at a stop sign. So the initial speed of the car is 0. So everybody should be able to do this. This is trivial. So this is what you should have written down. The mass of the truck times the velocity initial for the truck. That's the initial momentum. And that's got to equal the final momentum, which is the mass of the truck plus the mass of the car times V final. Okay? So you solve for V final, you can get the answer. Okay. What's the impulse, let's say, delivered to the car? Calculate the impulse delivered to, think about the impulse momentum theorem. Right? So the impulse delivered to the car is given by the change in momentum of the car. What was its initial momentum? 0. What's its final momentum? It's just m times vf. So the impulse delivered to a car is m vf. And then I can put in for vs what it equals. So that's m times mv initial for the truck over m plus m. So that's the impulse delivered to the car. Is that impulse towards the right? Let's say the truck was moving to the right. is that impulse to the right or to the left? To the right, right? It's in the same direction as the final velocity. What's the impulse delivered to the truck? It's just minus that. So there is a little bit of a connection between using conservation of momentum and using impulse and momentum. I'm going to talk a little bit about elastic collisions. So elastic collision, which is never perfectly achieved in macroscopic objects, but is pretty close in many. That means kinetic energy is conserved. How do you know if it's elastic? Really, you don't, all right? You have to more or less be told, or you can kind of sense it. So for instance, in billiards, the collision is pretty much elastic. When you hit a baseball, it's pretty much elastic. In car crashes, it's usually not elastic. Whenever two objects stick together, it is never elastic. That, in fact, is the most inelastic it can be. Inelastic, not elastic, right? Okay? So some cases, kinetic energy is conserved. Okay. I'm going to do a simple version of an elastic collision, and you can read in my notes a more complicated version in one dimension. And then on, what's today? Thursday. On Monday, I'll show you what happens in 2 dimensions. So we're going to look at 1D elastic, and we're going to assume same mass and one particle at rest. All right, so I'm going to write down conservation of momentum. So initially I have mv1 plus 0, because one particle is at rest, equals mv2 plus mv1 final plus mv2 final. Okay? If you want, we can write this as one initial. All right, so that can be easily written. Initial equals v1 final plus v2 final. Okay, pretty easy. Now I'm going to write down conservation of kinetic energy for an elastic collision. So I have 1/2 m v1i, I'm sorry, m vi v1i squared equals 1/2 m v1 final squared plus 1/2 m v2 final squared. All right, we can get rid of all the 1/2s and the m's. So we get v1 initial squared equals v1 final squared plus v2 final squared. All right, so the question is, how can I figure out something? What's the easiest thing to do to solve these two equations? And the answer is not solve for one and plug into the other. That's not a good one. The idea is, what's the easiest thing to do? The answer is square this equation. So if I square this equation, I get v1 initial squared plus v1 final squared plus v2 final squared plus 2v1. So look at this. Look at this. What can you conclude? This has to be 0. So that implies v1 final equals 0 or v2 final. All right. Which one's right? This corresponds to hitting one particle hitting the other, the first particle stopping, and the other particle going off with the velocity of the first particle. And that's what a collision usually is. This one corresponds to the first particle whizzing by the second without touching it. That's what this one corresponds to, right? So both solutions have a physical interpretation. Because nowhere in here is built in that the two particles actually collide, right? If I have a particle here and another going like that by it without touching it, those two equations are still valid. Okay? So each solution has a physical interpretation. Right? We will illustrate this during the discussion sections next Tuesday and Wednesday. We'll be showing this actually works, that this is true.